Alright, so this next little part, we're still in section 3.6, but we want to actually now start looking at specifically the inverse trig functions. Now, before we jump in and we start looking at actually inverse trig, I just want to remind you that, one of the techniques for finding derivatives of inverses, besides using the shortcut rule, was to basically, like for example, we had done this with the log function in e to the x, that in order to find the derivative of f inverse of x, which was equal to the log of x, that what we did in that problem is we thought of this as y equals ln of x. We switched to our inverse function, e to the y equal to x. And that when we did that, that's kind of like find the corresponding point. And that once we had that, then we took the derivative implicitly. I'm kind of showing you another way to find the derivative of an inverse. We took the derivative of this, so we did the derivative of e to the y with respect to x, and then we took the derivative of x with respect to x, which would give us derivative e to the y is e to the y, dy dx equals 1. Then we solved for dy dx. And notice that as soon as I solve, because I'm dividing it over to the other side, that here's where we're getting the reciprocal part. So we, just like we did when we did the shortcut rule, we found a corresponding point, which is kind of this idea. We did the reciprocal, and then at this point we went, well, wait a minute, the corresponding point part, this y, how do I find that y? Well, that y was ln of x. We go back to the function that we have, and then you basically simplified your rule, and that's how we got our 1 over x. But notice that what we did is we did 1 over the slope of the original function. We have our derivative of e to the y, which was e to the y, the reciprocal of the slope of the other function at the corresponding point, which is where we put back in ln of x, and then we had simplified. So keeping that same kind of pattern in mind, let's do this more in a general fashion, just to kind of show you that this works. So I have a function, y equals f inverse of x, right? And we basically know that according to that, we have the point on the inverse of x, y, on f inverse. Then, based on the fact of our definition of inverses, that we could also write this as x equals f of y, right? Corresponding point, which tells us that the point yx is on the original function f. So that's kind of just some given information that we're going to use. Now, what I want to do then is, in order for me to find the derivative of f inverse of x, so it's kind of our technique, to find the derivative of f inverse of x with respect to x, we're going to use x equals f of y, and then we are going to basically find dy dx implicitly, okay, just like we did with the inverse. So I'm going to take x equals f of y. I'm going to take the derivative implicitly with respect to x. Right? The derivative of x is 1. The derivative of f of y would be chain rule, would be f prime of y times dy dx using our nice little chain rule. We solve for dy dx, so dy dx equals the reciprocal of the slope on f at y, and then because we didn't want this in terms of y, we wanted it in terms of x, we then substitute back in our corresponding point, and y was f inverse of x. And that gives us the same formula that we were working with before, that in order to find, in this dy dx, that is the derivative of f inverse of x with respect to x. that to find the derivative of the inverse, you do 1 over the derivative of the original at the corresponding point. Okay, so just kind of showing you that we have that same procedure. All right, now let's talk about the inverse trig functions, a special case. A little bit of review first, making sure that you remember that none of our 6 trig functions are one-to-one. They fail the horizontal line test. So we have to restrict their domains, and the domain that we restrict becomes the range of the inverse, and so we call those the principal value ranges. And yes, you do need to go back and review your inverse trig and relearn your principal value ranges. That for the arc sine, when we flip the sine graph over, clearly not a function, so we restrict it so that the inverse sine graph would only be this portion right here, so that it would be a function. So our principal value range is negative pi over 2 to pi over 2 for the inverse sine. Okay. Our inverse tangent, and again we're going to reflect it over y equals x. We have asymptotes here at pi over 2 and negative pi over 2. We ignore these dotted sections down here, and the inverse is only this middle section in here. It has a principal value range of negative pi over 2 to pi over 2 also. Okay, and notice the parentheses instead of the brackets since there are asymptotes there. And our inverse secant, what we're going to do for the inverse secant is we're going to delete this half of that curve after we flip it. We're going to keep this asymptote here at pi over 2, and we're going to keep this section of the curve. So we're basically going to go for our inverse secant, we're going to go 0 to pi over 2, and then pi over 2 to pi. And that's what we're going to use for our PVR. So that's just reminding you what those inverse functions actually looked like when you graph them and what these principal value ranges are, which is going to be important. All right, this part that's kind of described here is not really that big of a deal for us because our textbook did not use that, but some textbooks will use a capital letter to denote the principal value range is being used, so we only want the inverse sine of negative, the inverse sine of 1/2. This would only be pi over 6. Versus if we were solving and I started with sine of x equals 1/2, find all values, they would do x equals lowercase inverse sine of 1/2 to designate that you were trying to find all, not just the principal value range. We didn't really stress that last year. It's just kind of a convention that you might want to be aware of. But in calculus, we are always going to be referring to the function. So we're pretty much just always going to use the lowercase, and it's always going to mean the function, and you're in the principal value range. All right, so now we're in the special case. We want to find the derivatives of the inverse functions. I'm going to show you 2 ways to get it, one using the shortcut rule and one using implicit differentiation. All right, so using the shortcut rule, okay, so remember that to find the derivative of the inverse at x, that it's going to be the reciprocal of the derivative of f at the corresponding point, which is find f inverse of x. Okay, so keeping in mind that when we're doing this problem, what we basically want to remember is that we're assigning f inverse of x is this arc sine of x, and f of x, then the original function would be sine of x. And we do remember that we have that principal value range that we're restricting it to negative pi over 2 to pi over 2. You'll see where that becomes important in just a second. All right, so I want to find, I'm going to write it this way, the derivative of arc sine of x with respect to x. So in order to find the derivative of this inverse, the derivative of the inverse, I'm going to use my rule. I'm going to do the reciprocal of the derivative of the original function. So the original function is sine, its derivative is cosine, of the corresponding point, which is the y value that you would get when you do f inverse of x. And y is arc sine of x, so this is simply arc sine of x. All right, now we're not done with this problem. We're going to come back to this. I'm going to show you the second way to get to this point, and then we'll talk about simplifying. All right, so number 2. Instead of applying this formula, the derivative of an inverse is the reciprocal of the derivative of the original at the corresponding point. What you can do is take your y equals arc sine of x. We can basically turn that to its corresponding value, which is x equals sine of y. We are then going to take the derivative of both sides with respect to x implicitly, and we're going to remember that it's implicit differentiation, and then we're going to solve for dy dx. So this ends up giving me 1 equals the derivative of sine is cosine of y times dy dx. I solve for dy dx. dy dx equals 1 over cosine of y, which becomes, again, because you're going to take out your y, 1 over cosine of arc sine of y. So a little bit longer method, but kind of the implicit differentiation view of how we get to this point, versus I'm just using the shortcut formula. The derivative of an inverse is the reciprocal of the derivative of the original at the corresponding point. Now we need to do some simplifying. That these functions will simplify because this is something that goes back to trig, and that you can simplify the cosine of the angle whose sine is x. That, a little bit of review, that if I want to find the cosine of the angle, and this angle, because of the principal value range, is negative pi over 2 to pi over 2. Whoops, come back here. Whose sine ratio is x, or we'll do this as x over 1. That basically we're going to draw triangles. Now, because we're between negative pi over 2 and pi over 2, when I draw my triangles, I'm going to draw them in quadrant 1, and I'm going to draw a triangle in quadrant 2. Okay, so the angle that we're looking at is either here or here. An angle somewhere that falls in this section. So then when I do my sine ratio, opposite over hypotenuse, so I'm going to consider this opposite and this hypotenuse. Opposite would be x, hypotenuse would be 1, and then down here, x and 1. Doesn't bother me that it's x and x. This would be the case if x is positive, then you would be in this triangle. If x is negative, then you would be in that triangle. So x itself will either be positive or negative, will decide which of these triangles that you're going to use. However, the nice thing about these triangles is that if I wanted to find the adjacent leg would be the square root of the hypotenuse squared minus your opposite squared. Good old Pythagorean theorem. So the adjacent would be the square root of 1 minus x squared. And it's not going to matter if x is positive or negative. This adjacent side right here is going to have the exact same value regardless of whether x is positive or negative. So it doesn't really make a difference in actually drawing the picture. A lot of times you can get away with drawing one picture and saying, hey, there you go, square root of 1 minus x squared. Now this is asking me for the cosine of this angle. And the cosine adjacent over hypotenuse, once I have the picture and I know hypotenuse is 1, opposite is x, and adjacent is now square root of 1 minus x squared, then the cosine of the angle whose sine is x, oops, and I just noticed I had a typo right there in this one. That should be an x. 1 over the cosine of arc sine of x, you're basically going to say, hey, the cosine of the angle whose sine is x would be adjacent over 1, so it would be adjacent square root of 1 minus x squared over 1, which is 1 over square root of 1 minus x squared. And it should make sense to you that this is a positive value because of the square root, because in quadrants 4 and 1 cosine is positive. So the actual rule that we are going to remember here and what we're going to memorize, because we're not going to go through this process every single time. If you will come down here and take a look at this, what you're going to do is add to your list of things to memorize that the derivative of the angle whose sine is x is 1 over square root of 1 minus x squared. And you will need to commit that to your memory. When we start doing all these functions and doing these derivatives, you are not going to want to recreate this wheel every time. You should be able to recreate this wheel because I'm going to ask you to do a proof for maybe one of these three. I'm going to show you the proof for arctangent and arcsecant, but I'm going to leave these as something that might be homework or something that you might see on a future quiz or test. All right? So what I'm going to do is let's go ahead and I think I need to add a paper, a blank piece. Yeah, I'm going to add a blank piece right before, and I'm going to do the proofs of the other two. All right, so I'm going to do the same thing. I'm going to use the shortcut rule. I prefer that over the implicit differentiation. And we'll talk about kind of what's different. So I want to take the derivative of the arc tangent of x with respect to x. All right, so I'm going to use the shortcut rule to find the derivative of an inverse. You do the reciprocal of the derivative of the original function, which would be tangent. Derivative of tangent is secant squared of the corresponding point, which is your arc tangent of x. So once we get to here, they're not going to leave this in. This is way too complicated. They're going to get rid of it and turn it into an algebraic expression. So we'll come over here on the side, and we'll remember that what we're trying to do, maybe I'll do one more step before I go to the triangle, is this is 1 over the secant of the arc tangent of x, and this whole thing is being squared. So what I need to do is I need to find the secant of the angle, and we are in our principal value range, which is negative pi over 2 to pi over 2, whose tangent ratio is x, or x over 1. So when I draw the picture for that, just like before, we're going to draw the picture in quadrant 1, and we have an option in quadrant 4, negative pi over 2 to pi over 2. Tangent ratio is x, and if you will recall, tangent is opposite over adjacent. So again, if x is positive, you would be here over 1. If x is negative, we would be here, again, over 1. And then, so to find the hypotenuse is the square root of the adjacent squared plus your opposite squared. So square root of x squared plus 1. And again, it doesn't matter whether x is positive or negative because we're squaring it here. So this would give me the same hypotenuse in either case. Right. So coming back to my formula, the rule that we have for that one would be 1 over the secant. Secant is your hypotenuse over adjacent. So the hypotenuse over adjacent would be square root of x squared plus 1 over 1, or 1 over square root of x squared plus 1. Right? And if you take a look at our little summary sheet here, there's our second rule that you're going to add to your list of things to memorize. Right there. The derivative of arctangent is 1 over, why did it become, what did I forget right here? Squared, because of that. And when you, excuse me, square a square root, we get 1 over x squared plus 1. So that finishes out our derivative of the inverse tangent. All right, one more. Let's cut this out. Now we're going to do the derivative of the arcsecant. So I want to do the derivative of the arcsecant of x with respect to x. Alright, so to do this, the derivative of an inverse is the reciprocal of the derivative of the original. So the original would be secant. The derivative of secant is secant tangent. Notice I'm putting parentheses because remember I have to put the corresponding point in here. The corresponding point is arc secant of x. So we got a little work to do on this one because I have to figure out the secant of the angle whose secant is x, and then I have to figure out the tangent of the angle whose secant is x. Our principal value range for our secant, PVR, little reminder, was 0 to pi over 2, and then pi over 2 to pi. So this one's a little different because I'm not in quadrants 4 and 1. I'm actually in quadrants 1 and 2. So when I draw my picture for this one, I am going to draw it in quadrants 1 and 2. So let's go ahead and draw our picture. I'm going to draw my triangle in quadrant 1 and quadrant 2. So I'm trying to find, let's do this one first. I want to find the secant of the angle 0, I'm just going to cheat a little bit, 0 to pi except pi over 2, because that was the asymptote. Secant of the angle between 0 and pi, except for pi over 2, such that the secant ratio is x. Alright, so when we're doing this, remember secant is hypotenuse over adjacent. Right? So in this one, hypotenuse, x, and then adjacent, 1. Right? And that's when x is positive. And then when x is negative, now we got to be a little careful about this, that the hypotenuse is always positive. The fact that this x is a negative number is not really because x, the hypotenuse, is negative. It's because the adjacent side is negative. Because when I'm in this quadrant, this would be negative 1. But this hypotenuse has to still be positive. So just to kind of fix that I don't want the negative to be, I'm going to basically take x, and if it's negative, I want the positive to be the hypotenuse, and then the negative is the adjacent side over here. Okay, so I'm going to try to think of, and we might as well go ahead and do absolute value of x there too, because if it was positive. That's a little weird little kind of caveat. Hypotenuse is always positive. So we want to make sure that we think of the hypotenuse as positive. Now, in general, when we're looking at this, this says find the secant of the angle whose secant is x. You almost didn't really need to think about this problem because the secant of the angle whose secant is x would just be x. So this part right here is really easy. Okay? And it would be positive if you're in quadrant 1 and negative if you're in quadrant 2. Now where the problem comes in is now I need to do the tangent. I can still use the same picture. I want to find the tangent of the angle whose secant is x. So the tangent is opposite over adjacent. Right? Now, the opposite, using Pythagorean theorem, would be the square root of the hypotenuse squared, x squared, minus the adjacent squared, 1. Right? So this is going to be square root of x squared minus 1. This would be square root of x squared minus 1. It makes sense that that's positive because you're going up for the y value. But now here's where we have a little bit of a concern. I want to find the tangent of this angle. Right? If that angle is in quadrant 1, tangent of the arc secant of x. So if x is positive, I'm in quadrant 1. That tangent would be positive square root of x squared minus 1 over 1. However, if x is negative, arc secant of x, if x is less than 0, then I'm over on this side, and then I get, well, the answer is going to be square root of x squared minus 1 over negative 1. So we actually get two different answers for that one, depending on if x is positive or x is negative. Right? But the other thing is that if I put these together, okay, so now I'm kind of got two scenarios going. So I'm going to come back to my derivative, and what we're going to do is we're going to break it into two cases. So now I'm looking at the derivative of the arc secant of x with respect to x, which was our 1 over the derivative of secant, secant of arc secant of x, tangent of arc secant of x, and I'm going to split this into two cases. The two cases are going to be if x is positive and if x is negative. Right? If x is positive, then we would have secant of arc secant of x is x, and your tangent of arc secant of x is positive, square root of x squared minus 1. All right, if we do the negative, secant of the arc secant of x is x, but the tangent of the arc secant of x is negative, so it would be negative square root of x squared minus 1. And you're like, wow, this is really complicated. But then I realized that what I have here is if x is positive, I have x here. If x is negative, I have negative. Oh, what does that remind me of? That reminds me of absolute value. Because if x is negative, a negative times a negative is positive. And if x is positive, obviously positive. You can actually turn this into one formula, absolute value of x, square root x squared minus 1. And so that's why over here in our little shortcut rules, all of a sudden this little rule here has an absolute value in it. It's because you have two different cases when x is positive or x is negative. Now, in terms of these formulas, these are the two ones that in AB Calc are going to be used the most. I'm not going to guarantee that this one's not going to come up or these over here, but 95% of the time, the two most important ones are going to be these two. All right? And then throw these in as some extras just to make sure, just in case that you have. Or you could gamble and not worry about those and then worry more about these two. All right, I'm going to stop the video there and we'll come back with a new video for some examples.